Hello dear students, welcome to the lecture 15 of Artificial Intelligence and Machine Learning course. So today we are going to see our last lecture of this course, which is unsupervised learning. Up until now, we have all seen supervised learning, classification. In classification, there are a finite number of classes which are known to us before we build our model or before we make our prediction. In unsupervised learning, the number of classes are unknown. Okay, here, based on attributes of elements, we try to cluster them. Like we try to compose classes from unknown elements with using their attributes such as their similarity or distance and such. Okay. So in supervised learning, we have labels to our model. Then we can use that model to predict new data into one of the learned labels. In supervised learning, given labeled examples. In unsupervised learning, there are no labels, just the data. And based on data, we cluster them. Okay.
Unsupervised learning, given data, i.e. examples, but no labels.
Okay. Okay. Unsupervised learning, we have just data without labels.
Given some example without labels, do something. Learn clusters, groups without any label. Customer segmentation, i.e. grouping.
This is used a lot in nowadays in every platform that the user itself, himself or herself is the product it is used. What I mean is, for example, you are using Facebook, then Facebook groups you into the segments or segments you into the groups, let's say, such as your age, your gender, and your mostly about your what you are interested in, so that Facebook can show you relevant ads, or it is same for YouTube or Google, whatever the service you are using, free mostly in most cases. So the customer segmentation is basically everywhere in today's world.
Image compression.
In image compression, it is used to decrease the size of image with, let's say, putting or reducing the number of bits without reducing the image quality not much. I think let's look for it. Okay. Hmm. Okay, image compression using K-means algorithm. Okay, they want account to read it. Okay, this method uses K-means algorithm, which we will see. So I will show you it in the further slides, and then we will read that article.
Bioinformatics, learn motifs. Find important features. Unsupervised learning, clustering.
Okay, okay, we have raw data, and we extract features, same processes as clustering. Then we group them. I mean same process as classification. Then we group them into the clusters based on their similarity or distance. Okay.
No, supervision, we're only given data and want to find natural groupings. Unsupervised learning, modeling. Most frequently, when people think of unsupervised learning, they think clustering. Another category, learning probabilities, parameters for models without supervision. Learn a translation dictionary. Learn a grammar for a language. Learn the social graph.
So these are not like clustering, and rather than they are learning parameters for models without supervision, translation, grammar, or social graph. This is also unsupervised learning.
Clustering. Clustering, the process of grouping a set of objects into classes of similar objects. Applications.
Gene expression data, you see, for gene modeling it is used a lot, and face clustering. With face clustering we can cluster faces. So in this example you see we cluster faces into the groups such as face 1. This image, and this image belongs to the same face, and this image and this image belongs to the same face, and this image belongs to this face group. It has only one image, this group. You see this is grouping people into the clusters, faces. You see it can be used a lot. Search result clustering. Here, when you look for Apple, they are clustered into the different groups, such as Apple of Word, Apple of Company, or other things. Or when you look for Xbox One, it groups you to Xbox One related articles. It is mostly used in e-commerce. For example, when you search for a product, Google or product search websites clusters products into the groups, which was also my both master degree thesis and PhD thesis. I tried to cluster e-commerce products into the groups. So, for example, when you search for a graphic card model such as GTA 1050 Ti, GTX 1050 Ti, my algorithm will try to bring you different websites that are selling GTX 150 Ti card. Okay. Clustering in search advertising, this is used a lot, as I said you.
Find clusters of advertisers and keywords. Keyword suggestion performance estimation.
Advertiser bidded keyword and 10 million nodes, for example. Clustering applications.
Find clusters of users targeted advertising exploratory analysis.
This is used a lot, targeted advertising. It is basically everywhere in nowadays. Every ads platform tries to cluster you into the group, therefore to show you most related advertisements so that you can purchase those advertised product, and both the advertiser and the product seller makes profit. Clusters of the web graph distributed page rank. I think it is now much more than 100 million nodes. Data visualization. Visualization.
Data visualization.
Okay, data visualization. It's hard to pronounce.
Wise et al. Visualizing the non-visual, PNNL.
Okay, this is an article. When it is writing like this, it is an academic article, and if you search for it, you will get it. Okay, so here, mountain height equal to cluster size, like this, and it is visualized like this.
A data set with clear cluster structure.
Okay.
What are some of the issues for clustering? What clustering algorithms have you seen used?
Could we cluster this data? Yes. Here a cluster, here a cluster, and here a cluster. It's a pretty distinct example. So what are the issues for clustering?
Representation for clustering. How do we represent an example features, etc. Similarity, distance between examples. Flat clustering or hierarchical. Number of clusters fixed a priori data driven.
This is actually the biggest problem in clustering. You don't know how many clusters there are. Okay, so your algorithm should be able to reach the certain number of clusters with as close as it is in actual reality. And this is the hardest problem of clustering. Okay, one moment. Okay.
Clustering algorithms.
Okay, so there are flat algorithms.
Usually start with a random, partial partitioning. Refine it iteratively. K-means clustering. Model-based clustering. Spectral clustering. Hierarchical algorithms. Bottom-up, agglomerative. Top-down, divisive.
Okay, so there are two kinds of clustering algorithms. First type is flat algorithms. They start with a random partitioning like this, then they refine it. For example, they split clusters or they merge clusters and such. And then there are hierarchical algorithms.
Hierarchical.
They can be bottom up or top down. If it is bottom up, they start with each clustering as each data as a single cluster, then they are merged when you go to the top. If you do top down, they start as a single cluster, all units, then they are divided. Okay, you see agglomerative and divisive.
Agglomerative.
And then there are
Hard versus soft clustering.
so hard clustering.
Hard clustering. Each example belongs to exactly one cluster.
So in hard clustering, no cluster can contain two examples, two data. The one data cannot belong to the two different clusters. This is hard clustering. And then
Soft clustering. An example can belong to more than one cluster, probabilistic. Makes more sense for applications like creating browsable hierarchies. You may want to put a pair of sneakers in two clusters, I, sports apparel, and E, shoes.
okay. So it depends on your problem. If your problem can support multiple clusters for a same unit, then soft clustering is better.
K-means. Most well-known and popular clustering algorithm. Start with some initial cluster centers. Iterate, assign, cluster each example to closest center. Recalculate centers as the mean of the points in a cluster.
So let's check an example of k-means. You see at the beginning we have no clusters and we have some data. Then we randomly initialize centers. For example, the algorithm chooses this one, and this one as center. Also by naming of it, you see we set the k, which means the number of clusters that we want to compose. So when you are using k-means, you have to have an idea of how many clusters there are. Okay. And then we assign nearest points to the center. They are assigned like this. So this one nearest to this one to this one, these ones are this one, and these ones are this one. Then we readjust the centers based on this assignment. So the new centers are assigned like this for blue, for red, and for the purple. Then after the reassignment of the centers, then we reassign points to the new centers of clusters. So you see this blue dot is now closest to this center, therefore now it is red, and blues are like this. Then we readjust the centers like this. Then we readjust the points to the nearest center, and now this blue belongs to the red. Then we readjust the centers, and new centers are like this. Then we readjust the points, and you see no more changes. So our algorithm of k-means is done. It is pretty simple yet strong algorithm.
Assign, cluster each example to closest center. Recalculate centers as the mean of the points in a cluster.
Okay.
Iterate over each point, get distance to each cluster center, assign to closest center, hard cluster.
This is a hard clustering algorithm right now.
Recalculate centers as the mean of the points in a cluster.
So here the distance algorithm is really important. How you calculate distance of your elements in your element space, data space. Okay, so this is the one of the most important part of clustering, how you calculate similarity or distance of your objects. Okay, so there are distance measures such as Euclidean, good for spatial data. So if you wonder what was the spatial data, the spatial data is let's see. Okay, what is spatial data? Okay. Okay, so the spatial data is related to geolocated data in machine learning as well. So for example, let's read this example.
One way to do it would be to get geolocated data first. For example, let's suppose that you want to build a predictive model of apartment prices at a given city. Choose the city and then pick few locations where you want to conduct your experiment. These should be stored as a list of longitude and latitude points or a list of WKB2 hashes, which is a GIS convenient format. Then, collect features on this grid of points that could explain apartment prices, number of nearby cafes, number of bus stops, average price in a 1 kilometer radius, exposition to sunlights, average noise in dB, and so on. Be as creative as you could. Once you have done this, apply any machine learning algorithm that you find appropriate. Be careful not to feed the grid positions to your model as features. That's it.
Why we don't provide grid positions? Because they are not a related feature to our aim. Okay. So it is good for geolocation related data, Euclidean algorithm.
Clustering documents, e.g. news data.
And the Euclidean algorithm is calculated like this. So when you compare the distance of two elements, for each feature you subtract them, you take their power of 2, then you take their square and sum of it. Okay, so this is the Euclidean distance. It is pretty simple distance algorithm, distance metric.
Clustering documents, e.g. news data. One feature for each word. The value is the number of times that word occurs. Documents are points or vectors in this space. When Euclidean distance doesn't work. Which document is closest to Q using Euclidean distance? Which do you think should be closer? Issues with Euclidean distance. The Euclidean distance between Q and D2 is large. But, the distribution of terms in the query Q and the distribution of terms in the document D2 are very similar. This is not what we want.
So you see, Euclidean distance doesn't work in this example because the features have high numeric differences. Therefore, Euclidean distance fails in this case. Even though they are similar, they have big numeric distances. Okay. So in this case, the cosine similarity is better. I will take a pause here. Okay. So rather than the numeric value as comparison as distance, now we can use correlated with angle between two vectors distance with using cosine similarity, and let's read it.
Cosine similarity is a similarity between 0 and 1, with things that are similar 1 and not 0. We want a distance measure, cosine distance.
Equal to this.
Good for text data and many other real-world data sets. Is computationally friendly since we only need to consider features that have non-zero values. Both examples.
Okay, so K means recalculate centers as the mean of the pointers in a cluster, and mean of the points in a cluster is calculated like this. So the difference between cosine and Euclidean, let's see. You see, one of them is distance and the other one is similarity.
One overview. In this tutorial, we'll study two important measures of distance between points in vector spaces, the Euclidean distance and the cosine similarity. We'll then see how can we use them to extract insights on the features of a sample dataset. We'll also see when should we prefer using one over the other, and what are the advantages that each of them carry.
Okay, so
2. Measuring distances in vector spaces.
I am sure that you already know what does vector space mean. Vector space means that we convert features of our objects into the vectors, and these features, vectors, are being our vector space.
2.1. What is distance? Both cosine similarity and Euclidean distance are methods for measuring the proximity between vectors in a vector space. It's important that we, therefore, define what do we mean by the distance between two vectors, because as we'll soon see, this isn't exactly obvious. Let's start by studying the case described in this image.
Okay, you see, this is a two-dimensional vector space. There is X line and Y line, and we have three data in this vector space. So how can we calculate their distances?
We have a 2D vector space in which three distinct points are located: blue, red, and green. We could ask ourselves the question as to which pair or pairs of points are closer to one another. As we do so, we expect the answer to be comprised of a unique set of pair or pairs of points.
This is the two-dimensional space, 2D vector space. So it has two features, these points.
If only one pair is the closest, then the answer can be either blue, green, or red, green. If two pairs are the closest, the number of possible sets is 3, corresponding to all two-element combinations of the three pairs. Finally, if all three pairs are equally close, there is only one possible set that contains them all. This means that the set with the closest pair or pairs of points is one of 7 possible sets. How do we determine then which of the 7 possible answers is the right one? To do so, we need to first determine a method for measuring distances. 2.2. Measuring distances with rulers. We can determine which answer is correct by taking a ruler, placing it between 2 points, and measuring the reading. If we do this for all possible pairs, we can develop a list of measurements for pairwise distances. By sorting the table in ascending order, we can then find the pairwise combination of points with the shortest distances.
And here they are Euclidean distance, square root 2, square root 3, and 3. And they are calculated by the taking points, the space they are represented in. So this is minus 1 and 1, 1 and 1, 2 and 3, 1 and 4.
In this example, the set comprised of the pair red, green is the one with the shortest distance. We can thus declare that the shortest Euclidean distance between the points in our set is the one between the red and green points, as measured by a ruler.
So this was a ruler-based distance measurement, and then
2.3. Measuring distances with goniometers. We can also use a completely different, but equally valid, approach to measure distances between the same points. Let's imagine we are looking at the points not from the top of the plane or from bird view, but rather from inside the plane, and specifically from its origin. If we do this, we can represent with an arrow the orientation we assume when looking at each point.
so these are the orientation of points.
From our perspective on the origin, it doesn't really matter how far from the origin the points are. In fact, we have no way to understand that without stepping out of the plane and into the third dimension. As far as we can tell by looking at them from the origin, all points lie on the same horizon, and they only differ according to their direction against a reference axis.
You see, this is the axis reference.
We really don't know how long it'd take us to reach any of those points by walking straight towards them from the origin, so we know nothing about their depth in our field of view. What we do know, however, is how much we need to rotate in order to look straight at each of them if we start from a reference axis. We can at this point make a list containing the rotations from the reference axis associated with each point. We can subsequently calculate the distance from each point as a difference between these rotations. If we do so, we obtain the following pair-wise angular distances.
Okay, so these are the angular distances between the points blue and red and green. So blue and red here, this is the distance. Red and green here, this is the distance, and blue and green here, the distance. Okay.
We can notice how the pair of points that are the closest to one another is blue, red, and not red, green, as in the previous example. We can in this case say that the pair of points blue and red is the one with the smallest angular distance between them. Note how the answer we obtain differs from the previous one, and how the change in perspective is the reason why we changed our approach.
You see, this is the result is completely different when we measure with a ruler. By the ruler, what do we mean? Let me show you. Okay, so these distances would be let's draw it like this: ruler based, as you can see, and ruler based, and the ruler based. Okay, so this is red, blue, this is red, green, and this is blue, green. This is the ruler based distance, and This is the perspective angular based distance here. Let me show you in another image. Okay, so let's show it like this. So this area is the distance between blue red, this is distance red green, and this is the distance blue green. Okay, let's continue.
Two point four. The generalization to higher dimensions. What we've just seen is an explanation in practical terms as to what we mean when we talk about Euclidean distances and angular distances. In the example above, Euclidean distances are represented by the measurement of distances by a ruler from a bird view, while angular distances are represented by the measurement of differences in rotations. Let's now generalize these considerations to vector spaces of any dimensionality, not just to 2D planes and vectors.
Okay, so these were two-dimensional, so they had only two features, this one and this one, as you can see, whatever you call it. For example, height and width of an object. Okay.
In R, the Euclidean distance between two vectors n is always defined. It corresponds to the L2 norm of the difference between the two vectors.
So
it can be computed as.
It is simply computed as x1 minus y1. So feature one of the x object minus feature one of the y object. Then feature two of the x object minus feature two of the y object. Then feature three of the x object minus feature three of the y object, and so. And then you take their square, their power 2, you sum them, and then you take their square root. Okay. It is extremely simple, fast.
A vector space where Euclidean distances can be measured, such as, is called a Euclidean vector space. Most vector spaces in machine learning belong to this category. This means that when we conduct machine learning tasks, we can usually try to measure Euclidean distances in a dataset during preliminary data analysis. Some machine learning algorithms, such as k-means, work specifically on the Euclidean distances between vectors, so we're forced to use that metric if we need them.
Okay.
A formal definition of cosine similarity. If we go back to the example discussed above, we can start from the intuitive understanding of angular distances in order to develop a formal definition of cosine similarity. Cosine similarity between two vectors corresponds to their dot product divided by the product of their magnitudes. If n are vectors as defined above, their cosine similarity is. The relationship between cosine similarity and the angular distance which we discussed above is fixed, and it's possible to convert from one to the other with a formula.
Okay, so this is the formula.
Euclidean distance and cosine similarity in the iris dataset.
We already know the iris dataset, we have seen it.
Clusterization based on Euclidean distances. Let's take a look at the famous iris dataset and see how can we use Euclidean distances to gather insights on its structure. This is its distribution on a 2D plane, where each color represents one type of flower and the two dimensions indicate length and width of the petals.
Okay.
We can use the k-means algorithm to cluster the dataset into three groups. The k-means algorithm tries to find the cluster centroids whose position minimizes the Euclidean distance with the most points. In red, we can see the position of the centroids identified by k-means for the three clusters.
Okay, so if you remember with classification based on the labeled dataset, we were able to obtain 100% success. However, if we don't have the labels, let's see how much we can do, obtain. So when we use the Euclidean distance, the centroids are being like this. Therefore, you see we have a lot of error. Why? Because the yellows and greens are intermixed, and it is impossible to separate them with these centroids.
Clusterization of the iris dataset on the basis of the Euclidean distance shows that the two clusters closest to one another are the purple and the teal clusters. We're going to interpret this statement shortly. Let's keep this in mind for now while reading the next section.
Okay.
Clusterization based on cosine similarity. As we have done before, we can now perform clusterization of the iris dataset on the basis of the angular distance, or rather, cosine similarity, between observations. Remember what we said about angular distances. We imagine that all observations are projected onto a horizon and that they are all equally distant from us. The picture below thus shows the clusterization of iris, projected onto the unitary circle, according to spherical k-means. We can see how the result obtained differs from the one found earlier. It appears this time that teal and yellow are the two clusters whose centroids are closest to one another. This is because we are now measuring cosine similarities rather than Euclidean distances, and the directions of the teal and yellow vectors generally lie closer to one another than those of purple vectors. This answer is consistent across different random initializations of the clustering algorithm and shows a difference in the distribution of Euclidean distances vis-a-vis cosine similarities in the iris dataset. Interpreting the clusterizations over the iris dataset. We can now compare and interpret the results obtained in the two cases in order to extract some insights into the underlying phenomena that they describe. Clusterization according to Euclidean distance tells us that purple and teal flowers are generally closer to one another than yellow flowers. This means that the sum of length and width of petals, and therefore their surface areas, should generally be closer between purple and teal than between yellow flowers and any others. Clusterization according to cosine similarity tells us that the ratio of features, width and length, is generally closer between teal and yellow flowers than between yellow and any others. This tells us that teal and yellow flowers look like a scaled-up version of the other, while purple flowers have a different shape altogether. The interpretation that we have given is specific for the iris dataset. Its underlying intuition can however be generalized to any datasets. Vectors whose Euclidean distance is small have a similar richness to them, while vectors whose cosine similarity is high look like scaled-up versions of one another.
Okay, now the real question comes in.
When should we prefer one over the other? The decision as to which metric to use depends on the particular task that we have to perform.
Okay, this is the key point.
Particular task that we have to perform. Some tasks, such as preliminary data analysis, benefit from both metrics. Each of them allows the extraction of different insights on the structure of the data. Others, such as text classification, generally function better under Euclidean distances. Some more, such as retrieval of the most similar texts to a given document, generally function better with cosine similarity. As is often the case in machine learning, the trick consists in knowing all techniques and learning the heuristics associated with their application. This is acquired via trial and error. The way to speed up this process, though, is by holding in mind the visual images we presented here. If we do so, we'll have an intuitive understanding of the underlying phenomenon and simplify our efforts.
Okay, so basically you can test each metric and see how well they are performing. So you also should have a strong and good working result evaluation process as well. Okay. So the conclusions.
In this article, we've studied the formal definitions of Euclidean distance and cosine similarity. The Euclidean distance corresponds to the L2 norm of a difference between vectors. The cosine similarity is proportional to the dot product of two vectors and inversely proportional to the product of their magnitudes. We've also seen what insights can be extracted by using Euclidean distance and cosine similarity to analyze a dataset. Vectors with a small Euclidean distance from one another are located in the same region of a vector space. Vectors with a high cosine similarity are located in the same general direction from the origin.
Okay, and I think this was a good example. Let's continue. Okay. K means loss function. Okay, let's continue from here.
K-means loss function. K-means tries to minimize what is called the K-means loss function.
It is calculated like this. Distance, sum of the distance between two objects.
That is, the sum of the squared distances from each point to the associated cluster center.
Okay, so the points distance to the cluster centers, and we get their sum squared distances.
Minimizing K means loss.
To minimize it, we reset the cluster centroids and the clusters belonging objects.
Does each step of K-means move towards reducing this loss function, or at least not increasing? This isn't quite a complete proof argument, but 1. Any other assignment would end up in a larger loss 1. The mean of a set of values minimizes the squared error. Does this mean that K-means will always find the minimum loss clustering? No, it will find a minimum. Unfortunately, the K-means loss function is generally not convex and for most problems has many minima. We're only guaranteed to find one of them.
Because it changes according to where you have initially defined your centroids. You see, at the beginning we defined certain number of centroids providing the value of k. Therefore, the results each time we obtain differences.
K means variations, parameters. Start with some initial cluster centers.
So this is our parameters, starting with initial cluster centers.
Iterate, assign, cluster each example to closest center, recalculate centers as the mean of the points in a cluster.
Also, we define which similarity or distance metric we will use.
What are some other variations, parameters we haven't specified?
Okay, so here they are.
Initial, seed, cluster centers. Convergence, a fixed number of iterations, partitions unchanged, cluster centers don't change.
So there are three convergence rules. A fixed number of iterations, let's say like we are saying 1000 iteration and no more. If partitions are unchanged, then we can say stop. If cluster centers don't change, then we can say stop. Okay.
K means initialize centers randomly.
If we initialize centers like this, what would happen? Okay, and how can we initialize centers better than this one? So it is about the seed selection.
Seed choice. Results can vary drastically based on random seed selection.
So you see, this word is important. It may change your algorithm performance drastically.
Some seeds can result in poor convergence rate or convergence to suboptimal clusterings.
Okay. We want to obtain the best optimal clustering, so there are common heuristics.
Common heuristics: random centers in the space randomly pick examples points least similar to any existing center. Furthest centers heuristic: try out multiple starting points, initialize with the results of another clustering method.
So random centers in the space in one way, randomly pick examples another way. Points least similar to any existing center. Furthest centers heuristic: try out multiple starting points, initialize with the result of another clustering method. Okay. So let's see the heuristics.
Furthest centers heuristic:
Pick a random point for 2 to k, point that is furthest from any previous centers. Okay. So this is a furthest centers heuristic. And let's see how it is done. So we pick a random point for the first centers, for example, this one. And then which would be the chosen next? It would be this one because it is the furthest one to this one. Then we choose another one because our value of key is 3. Therefore, we have to have 3 centroid. So the third centroid is this one because it is the one that is furthest from the both centers. Okay. Then the fourth one would be this one. So what are the concerns for this approach? If k is 4, which points will get chosen? This one, and this one, and this one, for example. Let's see. Yeah, this one, this one, this one, and this one. So basically these 3 are all belongs to each of them, each their cluster, and this one is just one cluster. Okay, it says
doesn't deal well with outliers.
so these are outlier data. Therefore, furthest point have weakness in data where we have outliers. Normally, we would like to compose 3 clusters. First this one, then this one, and this one. So then there is another algorithm.
K means plus plus.
Pick a random point and from 2 to k and 1 to n, k is the number of cluster and n is the number of elements. We get the minimum distance to any center, then randomly pick point proportionate to the s.
Proportionate to s.
How does this help?
Makes it possible to select other points. If hash points greater than hashtag outliers, we will pick good points. Makes it non-deterministic, which will help with random runs. Nice theoretical guarantees.
So let's see an example of k means plus plus. Okay, I will try to find a good example step by step if there is any. We can't see from here. Let's check the articles. Okay, k means plus plus algorithm. Okay, initialization algorithm. The steps are involved are, let's read it.
Randomly select the first centroid from the data points. For each data point, compute its distance from the nearest, previously chosen centroid. Select the next centroid from the data points such that the probability of choosing a point as centroid is directly proportional to its distance from the nearest, previously chosen centroid. I.e., the point having maximum distance from the nearest centroid is most likely to be selected next as a centroid. Repeat steps 2 and 3 until k centroids have been sampled. Intuition: by following the above procedure for initialization, we pick up centroids that are far away from one another. This increases the chances of initially picking up centroids that lie in different clusters. Also, since centroids are picked up from the data points, each centroid has some data points associated with it at the end.
So this is the intuition behind the k means plus plus. Let's see the implementation. And I am looking for, okay, here. So these are the data points, and then we have previously selected centroids and the next centroid. So currently we have no previously selected centroid, therefore we pick a random point like this. And then we pick the next centroid like this. This is the previous centroid. Then we pick this next centroid like this, and the next one like this.
Note, although the initialization in k-means ++ is computationally more expensive than the standard k-means algorithm, the runtime for convergence to optimum is drastically reduced for k-means ++. This is because the centroids that are initially chosen are likely to lie in different clusters already.
Okay, this is a good one, and let's see if there is any other one. Okay, no images. I think we can even find online example. K-means, okay, here. Not this one. Okay, here. So let's increase number of clusters, or okay, these are the data points. I think it is using cosine distance. Okay. Okay, so this is how it is done. Let's reload. So these are the data points that we have, and we have two clusters, and let's see how well it will be done. So at the, oh, this goes directly to it. So this is the initial assignment. Each point assigned to initial cluster points. Then at the second iteration, the centers will be reassigned. You see, now these are the new centers, and then the data points will be reassigned, and it didn't change. Therefore, we are done. If we increase the number of clusters like this, the new centroids will be assigned like this. Then new data points will be assigned like this. So this is how it is done. Pretty simple. And there are some good articles for k-means ++ that I have found for you. Oh, this is gone. Maybe we can find it somewhere else. If uploaded to somewhere else, we can find it, I think. Yeah, here. Here, scalable k-means ++ and some maths. Okay. Okay. Leoid algorithm initialization. And how do we set initial clusters? Anyway, oh, my article is gone. Okay, look, you can look for these ones at the home if you want. And k-means data clustering using C#. And another one. Oh, here at k-means ++ clustering. Okay, anyway, I will continue. So we have seen them. Then there is k factorial. I think this means that how many clusters there are. Yes. This is the key point.
How many clusters? Number of clusters k must be provided. How should we determine the number of clusters? How did we deal with models becoming too complicated previously?
So these many clusters are too many and these many clusters are too big. So there are many approaches. Actually, this is the real problem in clustering
Regularization.
and statistical tests.
K-means loss revisited. K-means is trying to minimize.
So what happens when K increases? Losses goes down.
Loss goes down. Making the model more complicated allows us more flexibility, but can overfit to the data.
Okay, so we can modify the loss as like this, and then
AIC penalizes increases in K more harshly. Both require a change to the K-means algorithm tend to work reasonably well in practice if you don't know K.
so what is this AIC if you wonder? So this is the regular loss and this is the AIC loss, and it penalizes K more harshly because as the K increases, since it is multiplied with the number of elements, your loss increases. Okay. In the BIC method, it is multiplied with the logarithm of n. And then there is statistical approach.
Statistical approach. Assume data is Gaussian, i.e. spherical. Test for this. Testing in high dimensions doesn't work well. Testing in lower dimensions does work well.
So based on your how many dimensions you have, you can use statistical approach such as Gaussian and
Project to one dimension and check. For each cluster, project down to one dimension. Use a statistical test to see if the data is Gaussian.
okay, what will this look like projected to one dimension? It would look like this. And if it is Gaussian, we can estimate the number of clusters. So this is another one-dimensional Gaussian distribution. Okay, so the solution would be something like this. Choose the dimension of the projection as the dimension with the highest variance. Okay. On synthetic data, split too far to one split, two splits, four splits. Okay, there is another paper if you want to read. And before, let's see the K-means time complexity.
K means time complexity. Variables, K clusters, N data points, M features, dimensions, I iterations. What is the runtime complexity? Computing distance between 2 points, e.g. Euclidean, reassigning clusters, computing new centers. Iterate.
Okay.
In practice, K means converges quickly and is fairly fast.
So the time complexities are like this.
What is the runtime complexity? Computing distance between 2 points is O, M, where M is the dimensionality of the vectors, number of features, reassigning clusters, O, Kn, distance computations, or O, Knm, computing centroids. Each points gets added once to some centroid, O, and M. Assume these two steps are each done once for I iterations, O, Iknm.
I think you know this notation, which is the lesson of analysis of algorithms you have taken. So these are the runtime complexity. Okay, before we continue, I want you to let's check out to how image compression is done with clustering. Okay, this was the article that we wanted to read.
Image compression using K-means clustering.
So GPX is an image compressing algorithm. I think you already know that.
This article illustrates one of the practical applications of K-means clustering algorithm. Using K-means technique, we will be compressing the colored image using its pixel values. First, let's look at how the colored images are stored. An image comprises of several very small intensity values, dots, known as pixels. The colored image is the image that includes color information for each pixel. In a colored image, each pixel is of 3 bytes containing RGB, red, blue, green, values having red intensity value, then blue and then green intensity value for each pixel. As you may have observed, the size of a colored digital image can be huge as each pixel requires 3 bytes or 3x8 bits intensity values. So, these images are often stored as the compressed images with lesser number of bits for intensity values and hence, lesser memory for storage.
Okay, so there are different bits of images. I will show you, bit depth of images. And what are the each bit, each pixel of an image. So from our university page, let's find a bigger image, maybe this one, or okay, for example, let's check this image. Okay, this is a JPEG image. I will copy it, I will paste it, or I will just save it first. It's a huge image actually, and let's save it to the desktop as a slider image. Okay, so this image is, let's see how much bytes. Okay, you see it is 6 million bytes. This is the real bytes of it. The other one is how much space it is taking on the space based on my bit variation on the space. Let's open the image with paint.net. Okay, so the image is, let's see, it is JPEG, and when I save as it, I can change its type: PNG, JPEG, BPM, TIFF, GIF, GGA. These are all different type of image algorithms, and when I save it as JPEG, I can change its quality. You see there are several subsampling. These are the methods, and if I sample it with best compression, its size increases with 100% quality, and if I change the quality such as this one, you see how much it is changing. So this is about compression and quality and optimal value. Also, we can change, we can see how much bit it is from, I think, here you see the bit depth of JPEG is 24, and therefore it supports up to 24 bit, and each pixel is like this. When I hover it, you see it becomes pixelated, and here now it is more clear. With color picker, I can see each bit's RGB values here. You see these are the RGB values: R value, G value, and B value. They are between 0 and 225, like this. So it is basically 8 bit, because with 8 bit you can have up to 256 values, and this is about it. All right, as you can see, it changes from here, and these are the hexadecimal code of each pixel. Okay, and I can also save it as, for example, as PNG, and I will change its bit depth You see it can be 32, 24 or 8-bit. When I make it 8-bit, it will support up to 256 different colors. Okay, this is what is it about. So let me save it as 8-bit. Okay, here let's open it in a different tab. Okay, so now we can see how it has reduced our colors quality. So let's compare two images. Okay, for this image, let's see from the eye, for example. Okay, 1100 zoom in and 1100 zoom in. Okay, you see how bad it looks when it is 8-bit because we have lost a lot of color quality. So many colors are removed and replaced with the closest color. Therefore, you see how different they are. Okay, let's continue to the article. I think now you have an idea.
Formally, image compression is the type of data compression applied to digital images to reduce their cost of storage or transmission. Before moving on to the implementation, let's go through the k-means clustering algorithm briefly. K-means clustering is the optimization technique to find the k clusters or groups in the given set of data points. The data points are clustered together on the basis of some kind of similarity. Initially, it starts with the random initialization of the k clusters, and then on the basis of some similarity, like Euclidean distance metric, it aims to minimize the distance from every data point to the cluster center in each clusters. There are mainly two iterative steps in the algorithm.
Okay, before continue, let's check the 8-bit image size. So it is smaller, you see 7 megabyte, and it can also be compressed because when you save as PNG, it leaves some unused thing in the file and they can be removed. However, it is lower. Let's continue.
A. Assignment step. Each data point is assigned to a cluster whose center is nearest to it. B. Update step. New cluster centers, centroids, are calculated from the data points assigned to the new cluster by choosing the average value of these data points. These iterative steps continue till the centroids cease to move further from their clusters. Now, we get several clusters separated due to some difference, while some data points are grouped together due to similarity. For illustration, let's look at the picture below. Look how the data points have been grouped according to their distance values.
Okay, so
K-means applied on images. In our problem of image compression, K-means clustering will group similar colors together into K clusters, say K equals 64, of different colors, RGB values. Therefore, each cluster centroid is the representative of the three-dimensional color vector in RGB color space of its respective cluster. You might have guessed by now how smoothly K-means can be applied on the pixel values to get the resultant compressed image. Now, these K cluster centroids will replace all the color vectors in their respective clusters. Thus, we need to only store the label for each pixel which tells the cluster to which this pixel belongs. Additionally, we keep the record of color vectors of each cluster center. Look at the original and compressed images below. Now, let's look at whether the image is really compressed. Earlier, each pixel was taking 24 8x3 bits to store its corresponding color vector. After applying this algorithm, each pixel only takes 6 bits to do so, as it only stores the label of the cluster to which it belongs, K equals 64 in our example. k equals 64 different color vectors can be represented using 6 bits only. Thus, the resultant image will have 64 different colors in its RGB color space. Note that the compression here will be lossy, i.e. the fine details in an image may get vanished after this compression. However, we can take relatively higher value of k to minimize this loss and make it as minimum as possible. Here, we have only reduced the number of colors to represent a colored digital image known as color quantization. However, there can be several different ways to achieve this target. Few other methods can be reducing the size of the image or reducing the intensity ranges of pixels or reducing the frequency of an image. The full MATLAB implementation of the discussed algorithm can be found on the GitHub link here. I'll recommend to go through this implementation and try it yourself too, as it will really solidify your concepts. If you found it helpful, please star and fork the repository. Open mouth smile.
Okay, now you know how it is used in image compression. GPX works differently than K-means. And
the JPEG compression is a block-based compression. The data reduction is done by the subsampling of the color information, the quantization of the DCT coefficients, and the Huffman coding, reorder and coding. The user can control the amount of image quality loss due to the data reduction by setting or choose presets.
okay, it's another methodology. So, what is a good clustering? Okay, let's see.
Internal criterion: a good clustering will produce high-quality clusters in which the intra-class, that is, intra-cluster, similarity is high, the inter-class similarity is low.
Okay.
How would you evaluate clustering?
The evaluation of clustering success is really important aspect of clustering, and it is not that easy. And so, how we will be able to evaluate success of a clustering? If we put all of them into a single cluster, can we count that we have achieved 100% accuracy? From point of view that we would have clustered each object correctly, put them into put the same objects into the same cluster. However, on the other side, we would have put different objects into the same cluster as well. So let's see it.
Common approach: use labeled data. Use data with known classes, for example, document classification data. If we clustered this data, ignoring labels, what would we like to see? Reproduces class partitions. How can we quantify this?
Okay.
Purity: the proportion of the dominant class in the cluster.
So, what does this mean? This means that the dominant class gets the label of that class. What I mean is, in cluster 1 there are two classes, blue and red. So the cluster 1 has more reds, therefore cluster 1 gets the label of red. And the cluster 2 there are 4 blues, therefore the cluster blue gets the label of cluster 2 gets the label of blue, and cluster 3 gets the label of green. Okay, so then we can calculate their purity like this. The purity of the cluster 1 is 3 over 4 because the 3 elements in the cluster are red and the cluster 1 belongs to the red label, therefore 3 over 4. The cluster 2 has purity of 4 over 6 and the cluster 3 has purity 3 over 5. So the overall purity is 0.672. Weighted average, we can also take the weighted average of clusters. and it is equal to 0.667. In the weighted average, we get their average with the number of total elements in each of them. And so what are the purity issues?
Purity issues. Purity, the proportion of the dominant class in the cluster. Good for comparing two algorithms, but not understanding how well a single algorithm is doing. Why? Increasing the number of clusters increases purity.
So I could put each element into a single cluster. Therefore, all of them would have 100 purity. However, it would not be something that I was expecting to achieve. Okay, so purity is not alone a good metric to evaluate the success of a clustering algorithm. Okay, let's continue. Okay. Okay, purity isn't perfect.
Which is better based on purity? Which do you think is better? Ideas.
I would say this cluster is better. However, from purity point, they are same. Okay. So purity is not alone enough for evaluating the success of a clustering algorithm. Then there is average entropy.
Average entropy of classes in clusters where P classy is proportion of class I in cluster entropy. Cluster equals P classy log P classy.
Okay. Common approach. So let's continue. So entropy of each class, let's calculate them. It is calculated like this. The entropy of the first cluster is 1. The entropy of the second cluster is 1.5. So we can say that the lower entropy having class is better. Okay. And problem with k-means. What problems there are with k-means clustering algorithm?
Determining K is challenging spherical assumption about the data, distance to cluster center, hard clustering isn't always right greedy approach.
Okay, what would k-means give us here? It can give us something like this when we assume spherical cluster. So it is wrong in this case because I would prefer this one as a one cluster and this one as another cluster. And another view, it can give us some clusters like this. Okay, so another algorithm.
Expectation maximization M, clustering, mixtures of Gaussians. Assume data came from a mixture of Gaussians, elliptical data, assign data to cluster with a certain probability.
So k-means produces these two clusters, but expectation maximization with mixture of Gaussians composes these clusters. You see, expectation maximization is much better for this specific problem. So as always in machine learning, there is not a single algorithm that would work best for your data set. For your problem, you have to choose, you have to find the best working algorithm. Okay, EM clustering.
Very similar at a high level to k-means iterate between assigning points and recalculating cluster centers. Two main differences between k-means and M clustering. 1. We assume elliptical clusters instead of spherical. 2. It is a soft clustering algorithm.
So you see, with expectation maximization, each element has multiple probabilities to belong different clusters. What I mean is that, for example, this point is 90% red and 10% blue. This one is red, 80% red and 20% blue.
Start with some initial cluster centers. Iterate, soft assign points to each cluster, recalculate the cluster centers. Calculate p theta c x the probability of each point belonging to each cluster. Calculate new cluster parameters, theta c maximum likelihood cluster centers given the current soft clustering.
So there is an example of EM. Start with some initial cluster centers. Step 1, soft cluster points. And then we obtain something like this. And then notice it's a soft probabilistic assignment. And recalculate centers of clusters like this. And then we reassign values. We do keep iteration, and we can then at the final separate them like this. Okay.
How do you define a Gaussian, i.e. ellipse? In 1D, in MD?
In one-dimensional and in m-dimensional, the formula is like this: parameterized by the mean and standard deviation variance. Gaussian in multiple dimensions, it produces something like this. So soft assign points to each cluster, calculate probability, the probability of each point belonging to each cluster. How do we calculate these probabilities? Just plug into Gaussian equation for each cluster and normalize to make a probability. And how do we calculate cluster sentence? What is the best fit Gaussian for this data? We call this a one-dimensional Gaussian equation. Okay, the maximum likelihood estimation is expectation is asked mean and variance of the data. So it is calculated like this. Let's read this one. Okay. Interesting.
M stands for expectation maximization. Expectation. Given the current model, figure out the expected probabilities of the data points to each cluster. P theta c x. What is the probability of each point belonging to each cluster? Maximization. Given the probabilistic assignment of all the points, estimate a new model, theta c. Just like NB maximum likelihood estimation, except we use fractional counts instead of whole counts.
Okay, similar to k-means, iterate, assign cluster each point close center expectation. Okay, and then recalculate, maximization. Iterate, each iteration increases the likelihood of the data and guaranteed to converge to a local optimum. Okay, expectation maximization is a
M is a general purpose approach for training a model when you don't have labels. Not just for clustering. K-means is just for clustering. One of the most general purpose unsupervised approaches can be hard to get right.
Okay, expectation maximization is a general framework.
Create an initial model, theta, arbitrarily, randomly, or with a small set of training examples.
Okay, use the model theta to obtain another model theta such that, i.e. better models theta increases log likelihood.
Let theta equals theta and repeat the above step until reaching a local maximum guaranteed to find a better model after each iteration. Where else have you seen M? M shows up all over the place. Training HMMs, Baum-Welch algorithm, learning probabilities for Bayesian networks, M clustering, learning word alignments for language translation, learning Twitter friend network, genetics, finance. Anytime you have a model and unlabeled data. Other clustering algorithms. K-means and M clustering are by far the most popular for clustering. However, they can't handle all clustering tasks. What types of clustering problems can't they handle?
If the data is non-Gaussian data,
Non-Gaussian data. What is the problem? similar to classification, global decision, linear model versus local decision, KNN, spectral clustering.
So there are several examples of spectral clustering like this or like this. Okay, this could be another clustering. There are 8 clusters and they are like this. So you can't use that for this one. There is also hierarchical clustering which works best in some occasions. Okay, this is about clustering and clustering evaluation metrics. Okay, performance metrics to evaluate unsupervised learning.
In some sense, I think this question is unanswerable. I say this because how well a particular unsupervised method performs will largely depend on why one is doing unsupervised learning in the first place, i.e., does the method perform well in the context of your end goal? Obviously, this isn't completely true. People work on these problems and publish results which include some sort of evaluation. I'll outline a few of the approaches I'm familiar with below. A good resource with references for clustering is SECourses' documentation page, Clustering Performance Evaluation. This covers several methods, but all but one, the silhouette coefficient, assumes ground truth labels are available. This method is also mentioned in the question evaluation measure of clustering, linked in the comments for this question. If your unsupervised learning method is probabilistic, another option is to evaluate some probability measure, log likelihood, perplexity, etc., on held-out data. The motivation here is that if your unsupervised learning method assigns high probability to similar data that wasn't used to fit parameters, then it has probably done a good job of capturing the distribution of interest. A domain where this type of evaluation is commonly used is language modeling. The last option I'll mention is using a supervised learner on a related auxiliary task. If your unsupervised method produces latent variables, you can think of these latent variables as being a representation of the input. Thus, it is sensible to use these latent variables as input for a supervised classifier performing some task related to the domain the data is from. The performance of the supervised method can then serve as a surrogate for the performance of the unsupervised learner. This is essentially the setup you see in most work on representation learning. This description is probably a little nebulous, so I'll give a concrete example. Nearly all of the work on word representation learning uses the following approach for evaluation: learn representations of words using an unsupervised learner. Use the learned representations as input for a supervised learner performing some NLP task like parts of speech tagging or named entity recognition. Assess the performance of the unsupervised learner by its ability to improve the performance of the supervised learner compared to a baseline using a standard representation, like binary word presence features, as input.
So let's see what methods there are in the documentation of scale-it learn, clustering performance evaluation, rand index there is. Okay, let's read it.
Given the knowledge of the ground truth class assignments labels underscore true and our clustering algorithm assignments of the same samples labels underscore pred, the adjusted or unadjusted rand index is a function that measures the similarity of the two assignments, ignoring permutations.
So rand index is the first one. There are the advantages of rand index. Let's read them.
Interpretability: the unadjusted rand index is proportional to the number of sample pairs whose labels are the same in both labels underscore pred and labels underscore true, or are different in both. Random, uniform, label assignments have an adjusted RAND index score close to 0.0 for any value of n underscore clusters and n underscore samples, which is not the case for the unadjusted RAND index or the V measure, for instance. Bounded range, lower values indicate different labelings. Similar clusterings have a high, adjusted or unadjusted, RAND index. 1.0 is the perfect match score. The score range is 0, 1 for the unadjusted RAND index and -1, 1 for the adjusted RAND index. No assumption is made on the cluster structure. The adjusted or unadjusted RAND index can be used to compare all kinds of clustering algorithms, and can be used to compare clustering algorithms such as k-means, which assumes isotropic blob shapes, with results of spectral clustering algorithms which confine cluster with folded shapes.
Okay, so there are also some drawbacks.
Contrary to inertia, the adjusted or unadjusted RAND index requires knowledge of the ground truth classes, which is almost never available in practice or requires manual assignment by human annotators, as in the supervised learning setting. However, adjusted or unadjusted RAND index can also be useful in a purely unsupervised setting as a building block for a consensus index that can be used for clustering model selection (TODO). The unadjusted RAND index is often close to 1.0 even if the clusterings themselves differ significantly. This can be understood when interpreting the RAND index as the accuracy of element pair labeling resulting from the clusterings. In practice, there often is a majority of element pairs that are assigned the different pair label under both the predicted and the ground truth clustering, resulting in a high proportion of pair labels that agree, which leads subsequently to a high score.
Okay, there's the mathematical formulation, mutual information based score. So there is another one, scoring, mutual information based score.
Given the knowledge of the ground truth class assignments labels underscore true and our clustering algorithm assignments of the same samples labels underscore pred, the mutual information is a function that measures the agreement of the two assignments, ignoring permutations. Two different normalized versions of this measure are available: normalized mutual information (NMI) and adjusted mutual information (AMI). NMI is often used in the literature, while AMI was proposed more recently and is normalized against chance.
Okay. And there are advantages and drawbacks. So homogeneity and completeness and V measure. Advantages and drawbacks. You see each one have some advantages and drawbacks, and this is the good one, I think, which takes into true positive and false positive. FMI score, this is used a lot. Let's see the advantages and disadvantages.
Random, uniform, label assignments have a FMI score close to 0.0 for any value of n underscore clusters and n underscore samples, which is not the case for raw mutual information or the V measure, for instance. Upper bounded at 1, values close to 0 indicate two label assignments that are largely independent, while values close to 1 indicate significant agreement. Further, values of exactly 0 indicate purely independent label assignments, and a FMI of exactly 1 indicates that the two label assignments are equal, with or without permutation. No assumption is made on the cluster structure, can be used to compare clustering algorithms such as k-means, which assumes isotropic blob shapes, with results of spectral clustering algorithms which confine cluster with folded shapes.
So what is the drawback of FMI-based measures?
Contrary to inertia, FMI-based measures require the knowledge of the ground truth classes while almost never available in practice, or requires manual assignment by human annotators, as in the supervised learning setting.
So you see, this has no actual drawbacks. It works on every dataset. However, only if you have some labeled ground truth examples. If you have them, you can use these to correctly evaluate your success. Okay, and there is another ones. So when you do a clustering, you can check each one of these scores and publish all of them so people can compare your different scores with their obtained results. And based on your data, you can pick the best one that represents your data. It is always about what you want to achieve and whether you can achieve it or not. So based on your data, based on your aim, the algorithm changes, the evaluation changes, and such. Okay. And let's see what other algorithms there are. So in this scikit-learn, there is k-means, affinity propagation, mean shift, spectral clustering, hierarchical clustering, dbScan optics, birch, and clustering performance evaluation, which we have seen. So k-means we already know that, and there is low-level parallelism, mini-batch k-means, and then there is affinity propagation. This is another clustering method. There is mean shift, spectral clustering, hierarchical clustering, and dbScan, optics, birch, and clustering performance evaluation. Okay, this is all about clustering. This was the last lecture of our course. So let's also see our final project details once again. Okay, and here I will open your project details. Okay, so project details.
A. Project Details 1. First of all, you will determine a project 2. As soon as you determine your project, you can start working on it 3. The project can be anything related to machine learning 4. You can use ready datasets or compose your own dataset 5. For ready datasets, look below sources.
Okay.
6. If you are willing to take your graduation project from me and also write a conference paper from your project, I accept a good project for both machine learning course and graduation project, so single project for both. 7. You can do the project either solo or as a 2-developer team.
Okay.
8. If you decide to do the project with one of your friend as a 2-developers team, both of you please email me and let me know that you want to work together. 9. The project has to be developed by using GitHub or Bitbucket code management systems. 10. You have to properly commit, push, merge, pull request, and such. 11. You can find necessary related information about code management on the internet. 12. You can use Git Bash or any program for code management. 13. You have to make a layout and summary of your project and ask me before starting it. So I will approve your project. 14. Send me your project layout and details by email, furkan.gözükara@toros.edu.tr. 15. You can do the project in any programming language with using any database management system if necessary, such as using C#, PHP, ASP, .NET, Python, MS SQL, MySQL, SQLite, etc. 16. The key issue of the project is, you have to compose the feature set yourself. 17. So the dataset you are going to use has to be raw dataset. 18. You will compose features, attributes and scale them yourself. To display the success of your project, you have to use tenfold cross-validation.
So your project will be classification based. If you prefer to do clustering based, then it is also fine, but it is harder. Clustering is harder to done than classification since it is unsupervised learning.
20. You have to write a project report and explain your project A. How did you find your dataset B? How did you process your raw data and composed attributes, features C? How did you scale your features, attributes D? How did you do 10-fold cross-validation and calculated the success rate?
Okay.
Which programming language, frameworks, libraries, algorithms, methods did you use? 21. In addition to the project, you will record a video which will be explained at the end of this document.
Okay, let's continue.
B. General things that needs to be considered. Every project will be controlled one by one. So if you cheat or bring a ready code project, you will get FF. There will not a final exam. Your grade will be based on this project. Thus, take this project very seriously and start working on it immediately. Look the internet for the parts that you do not know. Write your code with as many as possible explanations. What does do that code block? Of course, put those explanations into your code with comment blocks such as, or, asterisk asterisk. In C#, create an account on https://stackoverflow.com/ and ask there, or look for answers there.
Okay. Let's continue.
Also use Discord channel for communication. Latest project delivery date, end of finals, but you can also deliver at the Boutonleme exams 1. Lastly, everyone will record a very detailed video to explain the project. 2. Video will be recorded with OBS Studio in 1080p, high quality so that I can read explained code easily. Resolution. Three. It is mandatory to use microphone when recording and explaining the project verbally by speaking. 4. Turkish students can record the video in Turkish. 5. The project has to be made in English. 6. Non-Turkish students can also record their video in Turkish if their Turkish is better than their English. However, they should use English if their English is better than their Turkish. 7. When explaining your project, you need to explain every piece of your written code. 8. What does that particular code piece or that particular class or that particular method, etc. And how did you write it? 9. Moreover, you have to explain and show every feature of your application. So run your application and do example of every feature that your application have. Let's say you have applied SVM on text classification. Run your application and show how you compose model on which data. Then provide an unseen test data to your model and show its prediction is correct or not. 10. Then after you have to upload your video to the YouTube and set visibility as public or unlisted. 11. Because it has to be accessible. 12. Furthermore, add your YouTube video link to the project folder as text. 13. Finally, zip or RAR your entire project and upload to your Google Drive. After you get your Google Drive upload link, send me that link as email, furkan.gözükara@toros.edu.tr.
Instead of YouTube, you can also put your project into your Google Drive, I mean the project explanation video. So let me update that part of the project details. Because YouTube also reduces quality at somewhat degree. Okay, I think it is now better. Let's continue reading.
14. When sharing your Google Drive upload link as email, make sure that your upload's visibility is set correctly. Set it as who has link can view or download so that I can download it. 15. Everyone will be sending a Word or PDF document along with their final project files. This document will contain screenshots of your all comments to the lecture videos, all of the 14 lecture videos or more if we make. Take screenshots with high resolution. Your comment has to be clearly readable. Those who fails to send this document will be counted as not attended to the lectures. Therefore they will get FF.
Okay, if you have any questions related to the project details, you can contact me by my email or from our Discord channel, and hopefully you will do a great project and learn how machine learning or artificial intelligence in essence is being made, not just get the idea of movies that you see because they are usually not representing the real world. In movies, people are doing everything just with imagination or clicking some buttons or such. Usually they are not the reality, the truth. I am hoping that you will do a great project, and you know that the future is lying through the machine learning and artificial intelligence, intelligent systems. Therefore, if you develop your skills with machine learning and artificial intelligence, I am sure that it will benefit you greatly in your future professional life. Okay, end of the course. Hopefully see you next semester or in future. End of lecture.